Hello, error analysis. Here I'm going to tell you about how are we going to compute error. So theoretical part I've covered in other video. So here just I'm focused on the numerical part and all the formula associated with error analysis. Okay, so a general idea about is error is equal to standard value of a measurement minus measured value, means measured by us, value, or observed value, or experimental value, the experiment which we have performed. So that is how we are going to find standard. It is standard. It is the error in an observation. Okay. But the question is, if there is no standard value, means if we want to measure height of a person, so it would not be a standard measurement. So in such case, how can we be sure whether we have measured it correctly or not? Or mass of some object, so we have to be very sure whether we are correct or not. So in such cases, what we used to do, we take a number of observations and then we take mean of it. So in the theory of this topic, I already discussed it, if we want to arrange some error which are due to imperfect device or imperfect technique, so we can be very careful and we can use standard devices to sort out those errors. Those are called systematic error. Then there are random error, in which physical condition can affect. So in order to avoid those effects, what we can do, we can take number of observations and take mean of those observations. So if we take number of observations, then the chances of error get reduced by that factor. Okay, so first step is we are interested to find mean value, which we will call later on true value of measurement, or mean value of measurement. So understandably, if there are n number of observations, then the mean value, I will give a symbol a to it. So mean value, that is, I show the mean with this angular bracket. Mean value will be sum of all the observations divided by number of observation. This is our mean value or true value. Okay, so this is how we have obtained the true value. So next, moving on. Second step is absolute errors. Absolute errors means delta A1, delta A2, up to so on. The error associated with each observation. So these are absolute errors. So delta A1 is mod of this mean value or true value minus observed value. And this is how we are going to find error in other observations also. There is a debate in some books. They write it like A minus A mean, but doesn't matter because we are interested in modulus of that error limit. And in fact, if we record some error like -3, so we consider a worst case that if it had been appeared with this sign in this manner, so it could be appear in other way also, like in positive manner also. So each time whenever we get this error or uncertainty, we write it in terms of plus minus in order to be be prepared ourselves to a worst case, that if some observation is negative of some number, -3, as I have given an example, so we could believe that it could be sometime +3 also. So that is why we consider this error with just a number, and then we express it in terms of plus minus sign. Means it can be little bit more than this and little bit less than this also. Okay, so moving on, proceeding like this, there will be delta an, which will be a minus an. Okay, so these are absolute error, they're individual errors. Next is mean absolute error. If we are interested that, see, as this is now the mean value of the observation, so we'll imagine that this is the actual value. And if this is the actual value, then what is the actual error there? So same thing, we will do the same thing here also. So mean absolute error. Mean absolute error, the symbol for this is again angular bracket. Actually, angular bracket is a modern way, I mean, little bit scientific way to express it. Okay, now that is delta a1 plus delta a2 up to n delta an divided by n. This is mean absolute error. Next, fourth, then comes relative error. Okay, but before that, let me tell you, if there is some final result, we want to report some final result, then the value or measurement with error limit will be given by mean a and then plus minus mean of this delta a. So this is how we are going to report final answer, and most of the time you will see such type of expression in many of the questions. So next is relative error. So relative error is simply this error or mean absolute error. Simply error if standard value is given, one observation is given, otherwise we will use mean values. And okay, this is relative error. And then there is percentage error. So percentage error is simply relative error multiplied by 100. So here it is into 100. So this is the computational part of error in some observation. Right now I'm not giving you some examples of it, because in order to give you some examples, first we need to understand rounding of significant figures and the mathematical operation involving rounding off, truncation and all that. So that is why I'm just leaving it here. Moving on, there is propagation of error. I mean, how error propagates from one quantity to other. So we can also call it combination of errors. Okay. Case 1 for addition. If Z is some physical quantity which depends upon A and B by this relation, and if delta A is uncertainty or error in A, in the measurement of A, I'm writing it a bit shorter, so maybe some of the sentence would not make that correct sense, but the actual meaning is coming from this. Then this delta Z, the error limit, will also be the sum of their individual errors. For subtraction, let us suppose some other physical quantity depends upon some C, D by this relation, then delta Y is again the sum of their error limits. For both addition and subtraction, we are going to add the error limits. Here I can give you a short example for this. Like here, if there is a triangle and its sides are 3 3 centimeter plus minus 1 centimeter, it's a huge error, but for the time being I'm giving this example. And other side is let us suppose 3.2 or to save my time, I'm taking it also 3 centimeter plus minus 1 centimeter, and this also 3 centimeter plus minus 1 centimeter. Then its perimeter will be sum of all of them, means 3 plus 3 plus 3, and then plus minus, then their error 1 plus 1 plus 1. This is how we are going to report the answer, 9 plus minus 3 centimeter. And if it is the case of subtraction, maybe we want to subtract two displacements. So earlier displacement was S1, and that is 10 meter plus minus 1 meter, and S2 is let us suppose 5 meter plus minus 1 meter in opposite direction that of S1. So if it is toward right and it is toward left, then their resultant displacement will be S1 minus S2. If we have chosen direction of S1 as positive, then so it will be 10 minus 5. There's no issue with this, but the error limit will be added only. So that will give us 5 plus minus 2 meter. So for addition as well as for subtraction, error will always be added, because as I have told you that we consider worst case, and in a worst case situation it will go like that. We try to find the maximum error, whatever be the possible value of error in that observation. So if there is an error, it might get subtracted also, yeah, of course, but once again we consider the worst case. So here we can say that if we want to add or subtract, or we have to deal with only two quantities, then there will be not much amount of errors. But if we have to deal with large number of quantities, then the error will also increase. So this is how the error propagates. But now next thing is multiplication and division. I am covering them in as a single topic, not separately, because we know that division can be expressed in terms of multiplication and vice versa. So let us suppose we have some formula, some relation z equal to k, where k is some dimensionless constant, some number. Then a to the power x, no, x is not looking good. A to the power a and b to the power b. There can be c to the power c also and d to the power d also. I'm leaving them. Then remember, in such a case, delta z by z, I'm directly imposing this formula onto u, is equal to a delta a by a plus b delta b by b. That constant will not appear in the formula. And like in addition and subtraction, we were having that error part separately. Here we can't have that part separately. We can only have this relative error term. Why is it so? And that constant part will also be eliminated. Why is it so? Because there is a derivation for this. One more thing I want to add here. Here we take this as mod. I haven't mentioned it, but all the time you just imagine that these power are inside the mod sign. So it is always it is always positive in nature. And see, that is why I have said that this multiplication division both are alike. Means if the same formula would be like this z equal to k a to the power a divided by b to the power b, still that formula wouldn't change. A delta a by a plus b delta b by b. So it wouldn't change. So see from here, because we take, see, k a to the power a and b to the power minus b, but that minus will be taken care as in terms of positive only. So remember that. Okay, now if I a quick derivation of this will be helpful for you to understand this concept better. But for that, you need to understand few things. First, you need to understand the property log. Log is an alternative to exponents. So like we have root and square. So square of 2 is equal to 4. So root of 4 is equal to 2. So in the same manner log works. I'm not going into entire mathematics, otherwise it will be a different topic and video will go very long. So I'm just give you a brief idea for this. Generally you will see something like this log, and there is a subscript in which e will be written, that is natural logarithm, and you need not to worry about it. Most of the time whenever then it will appear with this as a base. Just this time just frame yourself, frame this thing in your mind that okay, something like this happens, deal with some power, we can use this logarithm form. So if there is a multiply b, then it can be written as log of a, means log is some kind of operator, and then plus log of b. Base is important. For different base, value will be different. So base, from the word base, you can easily correlate with, like if we say that this is 10 to the power 3, so this is exponent and this is base. So it is something like that. I'm not going into it again. There in mathematics you can just think about some of the function, and that's all. For the time being, that will be enough. Okay, log of a by b base e will be log a minus log b at the base e. And if there is log a to the power n, then that power will go in front, log of a at the base e. This is the one thing. Next thing is differentiation. So most of the students are aware about differentiation, but let me give you a general idea for this. Differentiation looks like this or this. Ultimately, whatever be there should be variables. So it is actually, it is not something like that we are cutting this and cutting this. No, it is just an operator, like we have root, like we have log. So such type of operator it is, and it changes. This is an operator. When it applies on this function, it changes it according to this rule. And now don't ask me that where this d by dx has gone. So like cube root of 27 gives the answer 3. So where that cube root sign has gone, so in the same way, because it get operated on 27, then the result is 3. So in the same way, this d by dx is an operator which has been operated on x to the power n, and it gave the answer n x to the power n minus 1. In the same way, here we will do only the variable will change, t, and so on and so forth. You can change. See, like we have done earlier, a plus b whole square, or x plus y whole square. Just the change of variable won't affect the basic structure of the formula. So here it is. And one more thing, d by dx of some constant will be 0. Remember this thing. Differentiation is something, variation of one thing with respect to other. If something is constant, then there's no variation in it with respect to anything else. So that will be 0. So here, if both are variable, both are same variable. If there is constant, there is a variable, then differentiation is 0. But what if there is some other variable? So first we will treat it as this variable, then it will be n x to the power n minus 1. But it is not y. So once again, dx by dy, we have to write this. And how will we solve this? So that is the question for other day. Just try to understand, try to memorize this formula. Okay, same variable we will end up with this. Different variable, we will end up with this. And if a constant, then answer is 0. This is how differentiation goes. In order to understand differentiation, about differentiation more, you can find some other videos. I have also a video on differentiation and integration. So because it is a completely different mathematics, but we are going to widely use in class 11th and 12th. In physics as well as in chemistry sometimes, and maths, of course, it is there. So okay, now step 1, because we have z equal to k a to the power a and b to the power b. So first step, we will take log both the side. So log of z base e, I'm not putting it again and again. So log k a to the power a b to the power b. So it is continuing, so I'm not writing it again and again. So log of k plus log of a to the power a plus log of b to the power b. Now next step is, oh, I didn't tell you the differentiation of log. So d log, let us suppose x by dx will be 1 by x, but if it is d log of y by dx, then it would be 1 upon y and then dy by dx. Keep all these things in your mind. So here it is. And now what are we going to do? We'll apply this exponent rule here. So it is log of k plus a log of a plus b log of b. Okay, now differentiate. We are differentiating with respect to, let us suppose z. We can differentiate it. There are, this is a variable, this is a variable, this is a variable. We are differentiating it with respect to z. So we'll write it like this: d by dz of log of z. Then plus, equal to d by dz log of k. Then plus d by dz a log of a plus d by dz b log of b. Actually, we have to do this thing separately and then take mod of it, and later on we have to come back. But here we'll imagine that we are taking mod. So it means if there is some negative power, it will come out as positive. Okay, so dz, d log z by dz, something like this. Both variables are same, so 1 upon x. So here 1 upon z. Then d log k by dz. This is a constant, so differentiation of constant is 0. That is why I have told you that the constant part will be eliminated. Now here this constant, it will not be affected, and this log a 1 upon a, it will be something like this, because variable are different. There is a, there is z. So 1 upon a, and then dA by dz plus then b, and 1 upon b dB by dz. Actually, I'm not saying that I'm cross multiplying it here. There is a certain different rule in mathematics to do that, but ultimately by some mathematical interchanges, we can do this. So why don't we do directly? So the explanation can be obtained in mathematics, but here we can directly do that. Think like we have cross multiplied it. So dz by z is equal to a, dz has gone there, so dA by A plus B dB by B. And in terms of, see, this is an error limit. So in general form, we can write delta z by z is equal to A delta A by A plus B delta B by B. And that was the original formula. So this is how we can proceed. Okay, other than that, if there is some this kind of form also, 1 upon z equal to 1 upon a plus 1 upon b. Till now you know about parallel combination of resistance in this form, but later on you will come to know that there are some other relations also in this form. So in such cases, how are we going to do? Because it is, we can't do it with this form. We can't do it. This is totally a different idea, different different way to solve this. So how are we going to do it? So again, we will take use of take the help of differentiation. Okay, now see, again we'll differentiate it with respect to z. So d by dz of z to the power minus 1 is equal to d by dz of a to the power minus 1 plus d by dz of b to the power minus 1. And the formula was dx to the power n by dx is equal to n dx to n x to the power n minus 1. Okay, so here it will be minus 1 and then z to the power minus 1 minus 1. So that will be minus 2. And here it will be minus 1 then a to the power minus 2. But remember that formula, when variables are different, then it will be dA by dz. Then instead of plus, that will be minus 1 b to the power minus 2 dB by dz. Okay, and again we'll cross multiply z here, but before that minus will get cancelled. If it not b, then still we would be taking its mod only. So now it will be z to the power minus 2 dz is equal to a to the power minus 2 dA minus b to the power minus 2 dB, or we can write it like this also, dz by z square is equal to dA by a square, plus it is, so dB by b square. In fact, there can be some relation like this also, z square is equal to 1 upon a square plus 1 upon b square. So again, you can go with the same way, and if I would help you, I can write it dz by z to the power 3 dA by a to the power 3 plus dB by b to the power 3, and so on. This is how we are going to solve such type of problem. We can modify such type of formula in terms of this error form. But from here dz can be obtained. In fact, dz can be obtained by multiplying entire this thing with z square, or in fact what else we can do, we can find relative error also. We can take one of the z there, so it will be dA by a square plus dB by b square multiplied by z only. Same thing we can do there also. So this is how we are going to see some of the formulae are already in a standard form, so we don't have to worry about it. But in such cases, what the way I have explained, we can derive the relation at a time, or we can just keep this thing in our mind. We can be very careful about, watchful about this, and we can do it. Okay, now moving on. Okay, so now one more thing. So we will go back to that expression where this z was equal to some constant k, then a to the power a, b to the power b, and this time I'm taking c to the power c, and so on. There can be number of terms. So as its solution is this, constant will be eliminated, delta a by a plus b delta b by b plus c delta c by c. So in such cases, we can say that this is the relative error in z, and this is relative error in a, and here also relative error in b, and here relative error in c. This is how we can solve such problems. There is a problem similar to this. In fact, we can find percentage error also. We can multiply this by 100. Now it is percentage error in z overall, and that will be equal to delta A by A multiplied by 100. This is the percentage error in A alone, and here B, delta B by B multiplied by 100. This is the percentage error in B, and then C, delta C by C into 100. That is the percentage error in C. So I'm giving an example for this also. Here it is. The question goes like this. If Z is equal to 2a square b upon root c d cube, then find relative error in Z. So that's so simple. Delta Z by Z is equal to, just eliminate this. So it will be 2a by a plus b power is 1. So delta b by b root c power is half. No need to worry about negative sign. So plus half delta c by c. And then for d, it is 3 delta d by d. And if in the same question, if it is given that if percentage error in A, B, C, and D is, let us suppose 0.5%, 2%, 2%, and let us suppose 1%, then find percentage error in delta Z by Z. So after expanding it like this, we would imagine, see, we can show it in if descriptive, if it is a descriptive question, but for MCQs we have to just apply that logic. We can directly put the values. So we can think about multiplication by 100 in each step, and then it will become percentage error. So the net percentage error in Z will be given by 2 multiplied by error in A is 0.5%, B is 2%, C is 2%, so there is 1 by 2 multiplied by 2, and D is 1%, and 3 into 1. So the overall answer is 1, 2, 3, 4, 7, 7% it is. So this is how we are going to solve such problem. But for in entire this discussion till now, I haven't given you any example for that initially what I have taught you. Just because till now there is not much discussion about significant figures or percentage or rounding off type of things, but now it is in this operation. Sometime in other also we have to be very careful about those mathematical operations. So now I'm going to tell you about some of the those mathematical part which we need to understand. Okay, so first we will start with the concept of least count. Why is it important? Because in many of the measurement, this least count is going to play an important role. So what is this least count is all about? So it is the minimum non-zero value to be measured by a measuring device. Why I'm saying non-zero value? Because some people can say that it has measured 0, but actually that is okay. By literature it can have meaning, but in physics it will zero measurement is not, it is not accepted one. So 0, yeah, of course it can be 0, but it shows that is because of the because there is no value there, or it is beyond the scope of that measuring device. So that is why I'm adding the term non-zero. Minimum non-zero value can be measured by a device. So for an example, for a stopwatch, sorry, not a stopwatch, generally our wristwatch, it has least count of 1 second. In modern day watches, it has reduced to 0.1 second also. And in stopwatches, I've seen it is up to 0.01 second. also. So it is resolving the time up to the 100th part of a second. So most of time, if you have seen in athletics, in racing, etc., if we have a watch of least count this, so many event would go tie. But if it is highly resolved, then we can see up to 10th place of second or 100th place of second, and then we can find that there's no tie if one was ahead of other. If it is still a tie, maybe there is a tie in that match, in that game, in that whatever it is. Okay, so that is the least count. In our common meter scale, the least count is meter scale. The least count is of 1 millimeter. And I hope now there are some other measuring devices like vernier calipers. Generally, it has a least count of 0.1 millimeter. And there is screw gauge. Generally, it has least count of 0.01 millimeter, and so on and so forth. There are so many devices. So now, what is the problem with this least count? This least count tells us that okay, let me give you an example of this meter scale. So let us suppose there's a scale. There is mark 10 centimeter, and then there are millimeter marks 1 2 3 4. Okay, let us suppose there is a rod up to here, it has been measured. So many of us will say that it is 10.123. It is 10.3, and some other would say that it is 10.4. But there would some other also, they would say that it is 10.35 centimeter. Now see, you must be surprised to hear this, that this value is accepted one, this is also accepted one, but this is not accepted one. Why is it so? Because the device which we have used has least count up to first decimal place only. So uncertainty begins with this place. Even this place is uncertain. So if this is uncertain, first uncertainty starts from here, then we can means this will be more uncertain with respect to this. So if there is already uncertainty, so why would we consider more uncertain part? So that is why we have to eliminate this. We can't expect this. We can either go for this value or that value, or if even we are taking the average of both, we have to round it off. Rounding off, I will explain you later on. Okay, now why I'm telling you about least count, because in the discussion of significant figure, it is going to play an important role. Now there are some rules of significant figures. What is significant figure? So most certain number in a measurement, and most certain digit in a measurement, and first uncertain digit in a measurement, and all the digits in between them are called significant figures. So first rule is, if there is a measurement and its reading is 4 3 6 8, let us suppose all of these are non-zero, so there are 4 significant figures. Means all non-zero numbers are significant. Okay, second thing, if now there are zeros, I told you that all non-zero numbers are significant, but here so does it have 4 significant figure? No, actually it has now 7 significant figure. Why is it so? Because all the zeros in between two non-zero digits are significant. So all right, one more thing, this is uncertain, first uncertain digit. Okay, this is most certain. Okay, now third one is with decimal place. Zero point 00273 it has only 3 significant figure. Reason for that is uh, actually if there is a decimal place, then habitually we put a 0 in front of it in order to explain that there's nothing in front of it. So this is not significant. In fact, these digits are also not significant. So only the significance starts from here. So and this is least significant figure. So decimal, I mean, no, first non-zero number and all the zeros on the left are not significant. Uh, Now, a very interesting thing. Again, in the same thing, if there is 0.002730, then it has 5 significant figure. Now you would say that what if we put some zeros here? See, here I am saying that if some data is given to you, some standard values have been given to you, it is not something like we are doing it. If some values are given to you, then how can you find that, okay, it is significant or it is not? So in those cases, what you can do, you can simply see whether if information is given in this way, then you will see that you will say that, okay, this value is resolved up to this level and up to this level also. So maybe it is a measurement, and maybe it is precise up to this level and up to this level. Okay. Next, fourth one is a bit tricky. Now, terminal zeros. Okay. I'm giving you two cases. One is okay, and other one is okay. So there is no decimal point given here. Can we write it like this? But if we write a decimal here, we have to put something after that decimal place. So if this is given, so it has definitely two significant figure. Terminal zeros are not considered as significant. But here, if there is a decimal place given, then all the trailing zeros, whether they are before decimal point or after decimal point, they are significant. So here we have 5 significant figures. Now, some people might contradict it with this. So here you can see there is no non-zero number in front of the first non-zero number. So this number is less than 1. So in such numbers, what you have to do, first non-zero number is most certain number. Okay, next. And see, this is what I'm telling you. They have come from some standard data, some standard results. So it is not something that I have written it. So by mistake, I have written something like, and you have to just count the significant figure in it. Significant figure means they are telling us that up to which level that value is precise. Okay. Now, there's another thing. It is called scientific notation or order of magnitude. Actually, order of magnitude is slightly different than scientific notation. So in scientific notation, what we do, we put a whole number. Oh, sorry, not whole number, a natural number. Before decimal place. In short, a number from 1 to 9 in front of decimal place, and after decimal place there can be certain numbers, and then multiply with 10 to the power some power n. This is the basically the representation of some big number or a small number. This is scientific notation. So I will give some of the example, like value of universal gravitational constant 6.67 into 10 to the power minus 11. Very small number. This is how it can be represented. So if a person can write it like this also, that is acceptable, no problem with that. But scientifically, it should be written like this. Okay, there's another one, like radius of Earth, 6.4 into 10 to the power 6 meter. So you can see this is how all the data you have given. So if it is in the higher power of 10, whether it is positive power or negative power, you will see that it is always given in terms of this scientific notation. Now there is order of magnitude also. So in order of magnitude, before that I will write one more. This is the charge of an electron. Okay. Oh, sorry, Newton meter square per kg square. Okay, now see, uh, here, in order to write it in terms of order of magnitude, actually order of magnitude means power of 10. Roughly how much power of 10 is included here. So it also goes like we do in rounding off. Later on I'm going to that part. So if this value is equal to 5 or greater than 5, then we are going to add 1 here. So then in terms of order of magnitude, it will be 10 to the power minus 10. And if here also it is also greater than 5, if it would be 5 also, then still we are going to add 1. So 10 to the power 7. Here it is less than 5, so it will remain as it is, 10 to the power minus 19. So this is how we write order of magnitude. And that is why generally you have seen that in science books, average height of human being in terms of order of magnitude is given as 10 to the power 0, which gives 1 meter. So generally human beings are not 1 meter tall, but they are about 2 meters sometimes 2.5 meter, sometimes 1.5 meter also. But here, in terms of order of magnitude, if it is 2 meter, then still we will write it 10 to the power 0. And since it is less than 5, so we have to just drop it down. So this is the order of magnitude for human height. Okay, so what I wanted to say here, so if some data is given in terms of this form, then the number of significant figures will be irrespective of power of 10. So only the number which is given here will be, only the digits given here will be significant. So like here, there are 3 significant figures, here 2 significant, here 2 significant figures. That's all. Okay, if we change the system of unit, the significant figure will never change. Like this, 6.4 into 10 to the power 6 meter. If I want to convert it in terms of centimeter, what I will do, I will write it like this, into 10 to the power 2 centimeter. So I should not do it this way. First thing, it is not the scientific method. So for such type of value, if I want to convert it into centimeter, I have to give these additional power of 10 to this exponent part. This is how we are going to do it. So keep this thing in your mind. Okay, I'm coming back because I missed this information here. This is 1.00. There were 2 significant figures. For terminal 0, I'm coming back because I missed that. But if the information of its least count is given, and if its least count, let us suppose, if its least count lies in ones place. So if it lies in ones place, then we are so sure. I mean, uncertainty begins with this place. Or I should write here tens place first. Least count is in tens place. Then there will be, see, then this place will also be certain. Then there are 3 significant figure. And if least count lies in ones place, then there will be 4 significant figure. So if in some of the observation, some of the value, some of the data, if they haven't mentioned the decimal place, and they have selected unit in such a way that you can't put a decimal there, but they have mentioned its least count also. Let us suppose mass of some object is 100 kg. And that's all, 100 kg. They are not saying 100.0. They are just saying 100 kg. And its least count is 2 kg, let us suppose. So it lies in one's place. So then there will be 3 significant figures. But all otherwise, if nothing is given in terms of least count, then in that case, that non-zero number will be considered as significant figure. Okay. Last thing, pure number, which are not the part of any observation. I mean, like if I write this area of a circle is equal to pi r square. So pi is 3.14 and up to so on. So it should not be considered like it has infinite number of significant figure, or it has 3 significant figure or 2 significant figures, or whatever given in the data sheet. We are not going to use it. We will consider it this pure number will always have infinity number of significant figure. Let me explain you once again. Like if in kinetic energy, half mv square, so this half is 0.5, but we can write it 0.50000000. So it can have infinite number. We can consider it to have infinite number of significant figures. Okay, pure number. All right. So now, before moving on, let me tell you something about rounding off also. So let us suppose we have a number a, b, c, d, like 2, 3, 7, 1. If this is a number, so this is ones place, this is tens place, hundreds and thousand. So it is not like a multiply b multiply c multiply d. So I'm considering it as a number where d is in ones place, c is in tens place, and so on and so forth. So okay, now if we want to round it off up to c, up to this place c, if c is to be rounded off, then after rounding off it should be replaced by 0. In fact, this d will also be replaced by 0. Now there are two cases. First, if c is greater than 5, if let me start with less than 5. If c is less than 5, like here, if c is less than 5, let us suppose it is also 3, then we are going to just drop it. We are just going to write it 0, and d will also always become 0. I mean, if we want to round it off up to b, then b, c, d all will become 0. And this b and a will remain as it is. There will be no change. Now see what will happen if c is greater than 5. If it is greater than 5, still it will be reduced to 0 because we are rounding it off. But then b will be increased by 1 and a will remain as it is until or unless b is 9. So if b is 9, that will also become 0 because it will become 10, and then the carry will go to a. So this is how it will go like. Okay, now anything else? Yeah, one thing. What if c is equal to 5? Okay, now this is a very tricky part, and I know the exactly reason why mathematicians have done it. Then we have to see two cases. First is whether this d, if this d is equal to 0, or d isn't there. Isn't there means the number is just ABC. So if d is 0 or d isn't there, then see whether b is even or not. If b is even, then just leave it as it is. And if b is odd, then increase it by 1. So, well, I don't know the actual reason why they have done it like this. And if d is equal to some non-zero number, then we are just going to increase it. This is meaningful. Then it is little bit tending toward B, means it is more than the actual, then it is meaningful ultimately. But here I don't know the actual reason, so I'm just leaving it as it is. So this is how we are going to round off. Now, significant figures, addition keeping significant figure in mind, in consideration actually. Okay, so here if we have some observations, some values to add, okay, let us suppose these are some of the numbers we have to add. So step 1, find the least number of decimal place. So here in this observation there are least number of decimal place. It depends upon least number of decimal place. So it has least number of decimal place, so it is up to 100th position. So all others, we are going to drop all others by suitable rounding off. So I'm rounding it off. So if I round it off, then there will be no effect on this. I'm not writing 0, 0, 0. It is understood. And here, that rule, this value is odd, so we are going to increase it by 1. Now it is 6, and it is 0. So this is done. So already I have drawn this line, so it means now I have nothing to do with these numbers. So see, this is, you have to be careful about, means in the question, in some of the question they can give some decimal number up to very large values. So what you have to do, you have to find least number of decimal place for addition as well as for subtraction also. Subtraction can't be of 3 numbers, so it will be of 2 numbers. So I'm not giving the example of that. That will be done accordingly, means least number of decimal places, and you can do it like that. Okay, so once again, here it is. It will be 16, then 13, then 6 decimal is there, 7, 5. This will be the final answer. That's all. But in the case of multiplication and division, we follow for multiply and division, we follow the least number of significant figure. Least number of significant figures. Let me give you an example. You know E equal to mc square. So you should know this thing, and later on you will be using it in class 12th in nuclear physics and all. So 1 atom mass unit is equal to 1 atom mass unit. You can read about it separately. 931 mega electron volt per c square. It will get multiplied here. So 1 atom mass unit will generate this much amount of energy. So let us suppose if there is a mass given, let us suppose I want to measure, they have given us mass of carbon 12 nuclei, which is 12.000000. You might wonder, you might laugh at it. So actually this shows that it is resolved up to 6 decimal places. There are 8 significant figures here, and there are 3 significant figures here. Okay, so what are we going to do? We are just going to multiply this with this. I have chosen this easy question in order to make calculation easy. So 12 ones are 12, 12 threes are 36, 37, 108, 111. So here it is, and rest are these decimal places, 6 decimal places. But remember one thing, this is not actually answer will be in mega electron volt. Okay, now just see one thing. We should report the answer with least number of significant figure. There are 3 significant figure. Least number of significant figure is 3. So 1, 2, 3. Rest of it we have to round it off, and we don't bother about these zeros now. So now, in fact, this decimal is not important now. 0, 0, and it will be increased by 2, 1, 1. That will be the mega electron volt, or more scientific notation, 1.12 into 10 to the power 4 mega electron volt. That will be the much better way to express the answer. This is how we are going to do these calculations, and this is how we are going to study this error analysis. Now, coming back to that part from where I have started, because at that time I have not given you an example of it. It is just because at that time I didn't tell you about the error analysis and rounding off type of things. So here, let us suppose we have given some observation. Let us suppose 3 observation. I'm taking lesser number to avoid workload. I mean, I'm doing it smartly, but maybe in the exam they will give 5 or 6 or more than that. What can we do about it? So let us suppose we have measured mass of something, a very light object. So it is, there are 3 readings of it, and they are 2.3 milligram, let us suppose, comma 2.2 milligram, comma 2.2 milligram. Okay. Now some people will say that this is the most appropriate answer. Yes, of course. But what we are going to do, first step, we are going to find true value. So these are masses, so I am writing m. So mod of m will be 2.3 plus 2.2 plus 2.2 divided by 3. So it will be 6.7 divided by 3. So it will give 2.23. And if we round it off, it will give 2.2, which is obvious result. But yes, it means rounding off worth it. So I mean, it is quite helpful. It is meaningful, I mean. So now we will find absolute error. I'm doing it here. So first error will be this minus this. This will be 0.1. So it is 0.1. And for others, it is 0. Oh, I think I have taken a wrong example. So let me make it little bit complicated. So I'm taking it 2.0. Now maybe we'll get a tougher value now. So it is going to be 6.5, and then oh, still it is 2.2 because of rounding off. Okay, but now few things will get changed, like last one. It will be 0.2, and the mean absolute error will be, add them, 0.3 divided by 3, it will be 0.1 milligram. Okay, then if they ask for final measurement with error limit, then it will be 2.3 plus minus 0.1 milligram. In fact, one thing I want to tell you, in fact, if they haven't given the value for least count, and if they ask give result with they give single one reading, and they give they can ask that to find value with error limit, then we can imagine that okay, at least the least count would be 0.1, then that will be taken care of like this. But sorry, this is not 2, this is not 2.3, it is 2.2. Final result is 2.2. Okay, And now in terms of relative error, it will be 0.1 divided by 2.2, so 1 by 22 it is. You can find it into decimal places or check the options what are given there. And percentage error, 1 by 22 multiplied by 100, so that will be 4.5%, I guess. So this is how we are going to solve such type of problems. So problems would be little bit complicated one also, and some of them would be related to some experimental work. So later on, I will make another video dedicated to some of the experiments from our syllabus. That's all.